Okay, to pick up where we had left off in the last lecture, we were talking about Hofmann elimination. So in Hofmann elimination, what we're going to do is we're going to start with an amine, and we're going to treat that with 3 equivalents of any kind of alkyl halide. Well, let's just say 3 equivalents of methyl bromide, and in the classical way that it's done, we use silver oxide as a source of hydroxide as we need it, and then we also typically use heat for this reaction. So what's going to happen is the 3 equivalents of the CH3Br are going to alkylate the amine so that we form our ammonium salt, and there'll be, in this case, a bromide as the counter ion. And then in terms of the treatment of this with the small amount of hydroxide and heat, we're going to lose one of the hydrogens on the carbon, and I'll say this correctly because I confused it last time, on the carbon with the most hydrogens, which means it is the least substituted carbon. That's where the double bond's going to form. So to form the major product, I am going to lose the H+, and I'm going to lose the amine as the leaving group, and I'm going to form then the double bond on the least substituted. I'm going to form the least substituted alkene as the major product. Okay. Now, there is a stereochemistry here that we need to take into account. Basically, this is still an E2 mechanism, only it favors losing the hydrogen from the carbon with the most hydrogens, with the least number of alkyl groups. So let's make this problem a little bit more complicated. Let's make it a little bit more complicated by putting let's put our NH2 group here. Let's put an H here. Let's put a CH3 group here, and then on the other side let's put a CH3, an H, and just for fun let's put an ethyl group here. And now let's treat this with our 3 equivalents of methyl bromide, our silver oxide, and heat. So we're going to do this under the Hofmann elimination conditions. Now, if we do that, what is going to be the major product of this reaction? Well, so ultimately, here's what I'm going to make. I'm going to convert the amine into an ammonium salt. Let's see, I need one of these to be bold. Let's make the methyl group bold over here. No, let's not make the methyl group bold. Let's make the ethyl group bold. Keep the methyl group where it is. Okay. So when I'm doing this reaction, here is my alpha carbon. I'm going to apply E2 to this. So there's my alpha carbon, here is my beta carbon, here is my second beta carbon. Now, this is the beta hydrogen that could be lost, and down here, each one of those 3 beta hydrogens could be lost. So, the question is, which one of those 2 beta carbons has the most number of hydrogens, since this is Hofmann elimination? And the answer is this one, the CH3. So when I treat this with my silver oxide and heat, the major product of this reaction is going to look like this. The double bond is going to form to the CH3 group. Okay, so if I'm writing this out as the mechanism, let me just change this and write this. Let's shrink it down. So what would happen is, if you think about this E2 happening, the OH comes in, grabs the hydrogen, pair of electrons moves, and then the ammonium leaves. So I'm going to form the double bond to the carbon with the most number of hydrogens, in this case the CH3. So I am forming the least substituted double bond. This will be the major product. And I'll ask you what the major product is. But I'm also going to ask you, what is the other possible product of this reaction? So I'm going to ask you to analyze this second beta carbon and tell me what the final product will be. Okay, and so this hydrogen right here, if I pull up my laser pointer, this hydrogen right here is going to also be lost. Now, because this is an E2 mechanism, I have to orient that hydrogen and the ammonium group to be anti-periplanar. And so that means this hydrogen will have to come down to the position where it's anti-periplanar to the leaving group. Okay, so if I do that, I'm going to have to rotate this hydrogen down, this methyl group up where the ethyl group is, and then move the ethyl group down into where the hydrogen is. So I'm going to need to reorient this molecule, which I will do down here. So I'll have my bold wedge, my dashed wedge, and my regular wedge. Up here I'm going to have my ammonium with the positive charge, my CH3, because now I'm going to remove that hydrogen that is on the second beta carbon, the carbon that has less hydrogens. And so in this case, I'm going to rotate the hydrogen down so it ends up here. I'm going to rotate the methyl group up into this position, and then I'm going to bring the ethyl group down here. So now I have the molecule oriented so that when the base, when the hydroxide comes in, grabs this hydrogen, pair of electrons moves, and then the amine leaves, I now have it oriented in the anti-periplanar geometry of the E2, required for the E2 mechanism. And so what that means is that the groups that are bold and the groups that are dashed will end up cis to each other. So remember, there are no bold and dashed wedges if you write the double bond out in the plane of the screen. So what will happen is the two bolds will be cis. That means methyl and methyl. And it means that the two dashed will be cis as well. So this is the minor product of the reaction. So a lot of times in the second product, I could say, are the two groups going to be cis, or are the two methyl groups going to be cis, or are the two methyl groups going to be trans? And so in this case, the only product that can be formed is having the two methyl groups cis. The other possible product, stereochemically, would be to have the methyl groups trans, like this, and that product is not formed. Only the product where the two methyl groups are cis is formed. Okay, so the first product, there won't be any stereochemistry to it, the major product, because in order to form the major product, you need to use the hydrogen or the carbon that has the most number of hydrogens, and so that will not ever be tertiary. It'll be secondary or primary. It's primary in this case. It's the other product. The way I give you this problem, it's the other product where I've shown you a chiral center. In other words, this carbon right here, it's that one that is the important, or is the one that has stereochemistry, because we have to orient so that the hydrogen is anti-periplanar to the leaving group, and then that will set up the stereochemistry where, again, the two groups that are bold become cis, and the two groups that are trans become cis as well. Sorry, the two groups that are dashed become cis as well. Okay? So that's the stereochemistry for the Hofmann elimination. And that's because it basically goes through an E2 mechanism with an anti-periplanar geometry. And that's what's critical about Hofmann elimination. Okay. Now, there's always a counter reaction, and that is what is called cope elimination. And so in cope elimination, we are going to do something similar. Let's not deal with stereochemistry first. Let's just go back and look at our amine that we started with Hofmann elimination. In this case, what I'm going to do is I'm just going to do two equivalents. I'm going to add two equivalents of methyl bromide to that nitrogen. And in this case, we might want hydroxide to do this reaction. So that means, what am I going to do? Well, first I'm going to, just to go through the whole procedure again, I'm going to alkylate the first methyl group on the ammonium and make the ammonium ion. Then I'm going to treat that with hydroxide so that it comes in and deprotonates the ammonium so that I form the amine. I'll go ahead and put the lone pair back in. Go ahead and put my lone pair in there. Then I'm going to treat this with a second equivalent of methyl bromide. So that now I make again the ammonium salt. And I'm now going to treat that with a second equivalent of hydroxide to make the tertiary amine. Now, before I made the ammonium salt, that's not how cope works. Cope only allows us we have to form a tertiary amine, which means we don't alkylate it the third time. So I'm just going to stay here. Now what I'm going to do is now I'm going to treat that amine with an oxidizing reagent, with an oxidizer. And the oxidizer that I'm going to use is our old friend, the peroxy acid. And you can use a lot of different oxidizers for this. You could use hydrogen peroxide. There's probably other ones that are shown in the Top Hat textbook. But what we're going to do is we're going to oxidize that amine. So what we're going to do is we're going to form then the nitrogen with two methyl groups on it. And it's now going to add an O- to that. And so this is what is called an amine oxide. And I believe an amine oxide was shown in the Top Hat book in the sort of reductive amination when you made when you made the imine or the Schiff base they talked about adding water and making the amine oxide. But this is what that's called. So you have to oxidize, you have to add an oxygen to the nitrogen to make the amine oxide. Now, what happens with the amine oxide is this. It's actually a decent leaving group. So what happens is that the hydrogen, that is on the beta carbon. So in other words, the group with the amine is the alpha carbon, and then we have these beta carbons with beta hydrogens. What's going to happen is you're going to get the same regioselectivity that you get with cope, meaning that you're going to form the least substituted double bond. Now what's going to happen is that nitrogen, that oxygen on the nitrogen is going to remove the beta hydrogen. So I need to rewrite this down here. And here's how I'm going to write it. I'm going to have the O- here, along with the two CH3s here. Oh, and I forgot that nitrogen has a positive charge. So if you were like, where's the positive charge? It's there. Okay, so I'm going to form that. I'm going to write it that way. Now what happens in this case is that the O- will preferentially remove the hydrogen off of the carbon with the most hydrogens again. So you can think about, again, this conformational issue. But now what's going to happen is that O- is going to grab this hydrogen, that pair of electrons is going to move down, and then the pair of electrons is going to go to the nitrogen. So what I'm going to do is I'm going to do a periplanar reaction, so that the amine oxide group that's leaving has to be periplanar to the beta hydrogen that's being removed, because that's essentially what we have. Okay, so I'm going to form this 5-membered ring. Again, to the carbon with the most hydrogens. And so what happens then is I form the same product that I did before with the double bond, and the amine oxide now becomes what's called a hydroxyl amine. And that forming that hydroxylamine makes a pretty good leaving group. So again, the regioselectivity is that we're going to form the least substituted alkene by the amine oxide removing a hydrogen from the carbon with the most hydrogens, and it does so by a periplanar reaction, so that the amine oxide and the hydrogen have to be in the same plane. Okay, and that's exactly opposite of the Hofmann elimination, because in the Hofmann elimination the leaving group had to be anti-periplanar to the beta hydrogen. In this case, this is what would actually be called syn periplanar, because syn means basically cis are on the same side. Okay, so that's where the reaction is slightly different. It's not slightly different, it's hugely different when it comes to the stereochemistry. So what I want to do is, to talk about the stereochemistry, let's do this. Let's use the same molecule that we did before, only now let's do a cope elimination from it and see how the products would differ. Okay, so we had our amine, hydrogen, methyl, and our ethyl hydrogen amine. So let's write that structure out that we had done before. So we had an NH 2 here, we had a hydrogen there, and we had a CH3 here. On the other side, we had an ethyl group, the hydrogen, and the methyl group. And let me just go back and make sure of that. Yes. Okay, so now let's do a cope elimination on this and write the major and the minor product. So what I'm going to do is I'm going to take and I'm going to now treat this with 2 equivalents of methyl bromide and hydroxide. I don't think silver oxide will work for this because I think the silver oxide will mess up the oxidation reaction. But this is essentially the same thing. So that's going to put me in a position where I've now converted my amine into now a tertiary amine. So it only has 2 methyl groups. Again, no positive charge. And the other carbon is going to remain the same because nothing happened to it. So I'm going to have my ethyl group. Okay, so now I'm going to treat this molecule with peroxy acid to oxidize the amine into the amine oxide. So let me do that down here. I'm going to end up with the nitrogen with the O-, the nitrogen plus, and then a methyl group on each side of the nitrogen. And then same stereochemistry as before. Now I'm going to put the CH2 with the H in because we're going to remove that beta hydrogen. Okay, so there's my amine oxide. So because I'm forming a 5-membered ring, the amine oxide is going to remove a beta hydrogen. So here's my alpha carbon, my beta carbon, my second beta carbon. Here's the beta hydrogen. Here is the other beta hydrogen that can be removed. Just in case you're thinking you want to remove this hydrogen, that hydrogen's an alpha hydrogen. It's not going anywhere. And the other hydrogens on the other carbon, those are all gamma hydrogens. So they are not, only the beta hydrogens in the boxes are going to be able to be removed. Now, what's the major product of the reaction going to be? The major product of the reaction is going to be the O-, removing the hydrogen from the carbon with the most hydrogens, pair of electrons moving down here, kicking off the amine oxide and forming the hydroxyl amine. So the major product of this reaction is going to be the same major product that we had before. Double bond's going to form to the CH2 group, and we'll have the hydrogen, the alpha hydrogen up there. Okay. So this is going to be the major product of the reaction. What about the other beta hydrogen? What happens there? Well, now I need to rotate this hydrogen right here. I'm going to need to rotate that hydrogen up and make it periplanar to the amine oxide. So that means I'm going to have to do not a 60 degree or not 120 degree rotation, but only a 60 degree rotation. So let me rewrite the right hand carbon down here. I'm going to point the O- this way. With my hydrogen on my bold wedge, and the CH3 group, because I'm not removing that hydrogen on the bold. Now what I need to do is I need to rotate this hydrogen and make it planar to the group rotate the ethyl group down so it's forward and down, and then move the methyl group back so that it'll go on a dashed wedge. So when I rotate that, it's going to look like this. My hydrogen is going to be in the plane. My bold wedge is going to have my ethyl group, and on the dashed wedge is going to be the methyl group. Now, just quick review, when we've used these sawhorse kind of models in the past, the question would be, what is this carbon-carbon orientation? What is that in a Newman projection? Now, up here, if we look down this bond, in this Newman projection, it would be staggered. So down here, this is actually going to be in the eclipsed Newman projection. Okay. And I'll write that after we do the reaction. So it's going to be eclipsed. So what's going to happen is the O- is going to grab the hydrogen, the pair of electrons is going to move here, and then that pair of electrons in the carbon-nitrogen bond is going to go to nitrogen. So again, I'm going to form a carbon-carbon double bond to the second beta carbon. Again, this is going to be the minor product. And so in this case, again, everything that's bold is cis. On the same side of the double bond, everything that's dashed is also cis. So the minor product of this reaction is going to have the methyl groups trans. Exactly the opposite of Hofmann. But yet Hofmann and Cope both form the double bond as the major product, the double bond that is least substituted. Okay? So let's draw out. So if I'm looking down this bond, just to kind of finish the story, as I'm looking down this bond, I'm going to see a Newman projection that looks like this. On the carbon pointed towards me is going to be a hydrogen up, the ethyl group on the right, and the methyl group on the left. Eclipsing this hydrogen is the amine oxide group. The hydrogen and the methyl group are eclipsed, and the methyl and the ethyl group are also eclipsed. So that means the amine oxide with its two methyl groups, its positive and negative charge are there. Down here, the ethyl group is going to be eclipsed by methyl, and the methyl group is eclipsed by hydrogen. So this is my eclipsed Newman conformation. And what happens, you can see that as you lose these groups, everything flattens out so that the methyl and hydrogen and the methyl and the ethyl group are the groups that are cis to each other on the double bond. Okay, so that's Cope elimination. So what's similar about Hofmann and Cope is that they both produce the double bond that is least substituted. What is different about Hofmann and Cope is that Hofmann goes through an anti-periplanar geometry and Cope goes through a syn periplanar geometry. But both will give the same major product, which is the double bond to the least substituted, or the carbon with the most hydrogens. Okay, so that ends chapter 23. And what we want to do now is move on to chapter 24. And in chapter 24, we're going to talk about carboxylic acids. We only have chapter 25 and 26 left. So we're getting close to the end. Now, there is some naming that they start with in the top hat chapter, naming carboxylic acids. I will move, or by the time you watch this, have moved the naming sheet that I had from before, from first semester, into the folder for today's lecture, so that you can have that in terms of priorities. If I get time, I'll redo a very quick naming video on the basics of naming. If you're overly ambitious before I get to that point, you can always go back to the Chemistry 221 Canvas site and look at one of the videos from chapters, I believe, 2, which is where we covered naming of all the different functional groups. Carboxylic acids are near the highest priority group that we have on our chart of functional group priorities. Okay. But we want to move to reactions, and actually what we want to do is we first of all want to talk about syntheses, ways to synthesize carboxylic acids. And before we talk about that, we should talk about, or before we talk about new reactions, we should talk about old reactions. So we are going to use review reactions. And if you take a guess what's going to happen, here's what's going to happen. The quiz for this lecture is the online quiz is going to give me the reagents. You're going to give me the reagents that you use for the following review syntheses of carboxylic acids. So, question number 1. If you have a primary alcohol, what do you use to form a carboxylic acid? What reagent do you use? You just need to give me one. There are many. Question number 2. If I had a double bond, how could I convert that double bond? How could I cleave that double bond into a ketone? And on the other side, a carboxylic acid. What reagent would I use for that? And there may be more than one there as well. Just give me one. Question number 3. If you had an aldehyde and an aldehyde only, what reagent would you use to convert that aldehyde into a carboxylic acid? You probably need 2 here. Now there's 2 different reagents, so let's be a little bit more specific. What reagent would you use that gives you the silver mirror? And question number 4 is, what's the name of that reaction that oxidizes only an aldehyde and gives you a carboxylic acid and the silver mirror? Okay, there's another one. Question 5. So question 5, if I take that same aldehyde, how can I oxidize it to a carboxylic acid? And in this case, it gives copper oxide, which is the brick red precipitate. What reagent do I use there? And what's the name of that reaction? Again, these are all review reactions to make the carboxylic acid. Question number 7. If you have a triple bond, what reagent would you use to cleave the triple bond to form two carboxylic acids? Question number 8. What reagent do you use to convert an alkyl benzene into a benzoic acid? Question number 9. Imagine I have this compound and I want to convert it to this alpha hydroxycarboxylic acid. Now, I'm gonna be very specific. Question 9 is what reagent would you use to accomplish that reaction? Question number 10 is, what is this molecule called? What's its name? Okay, now we're up to question 10. These are all review reactions. If I had a Grignard, what would I add to that Grignard? Then adding H plus H2O to it to make the carboxylic acid. What would I react there? So, well, that's not question 10. Sorry, that's question 11. So the first 11 questions on the quiz, and there may only be 11. We'll see what I do. I might add a few more questions to the quiz. But the first 11 are going to be giving me the answers to these review syntheses of carboxylic acids. Okay. And there'll be more, but right now we're just synthesizing carboxylic acids. Okay. Are we done? No. Now let's talk about sort of a setup of the carboxylic acid reactions. And we're going to find that there's a number of carboxylic acid reactions that we can do. We could set this up like what kinds of reactions do we already know about? Oh, good. We'll continue on. Review carboxylic reactions. So let's see, now we're up to question 12. If I want to convert a carboxylic acid to a carboxylic acid chloride, what reagent do I use? You might want to look at some of the other lectures because I put big X's through reagents that will not work. So make sure you do not give me one of those reagents. How else? What other reactions do we know? Oh, we know this. We know this from lecture and lab. Question number 13 is going to be, what is this reaction called? What's its name? If you don't know that, you're really hurting, because we did it both in lecture and lab. What else? I think that'll be it for the moment. So there will be no question 14. Okay, now here's what we can do to kind of set up some of our reactions. Oh, wait. I can convert a carboxylic acid into a ketone. What reagent would I use to do that reaction? It's not that far back in the past. It's within a week or so. So I reserve the right to throw in another reaction here, but let's talk about what we're going to do mostly with carboxylic acids, and more importantly, what is going to set up for chapter 25. And that's the following. I can convert a carboxylic acid into what is called a carboxylic acid derivative. Okay. So I can convert a carboxylic acid into a carboxylic acid chloride, into a carboxylic acid anhydride. So this is the acid chloride. This is the acid anhydride. I can convert it into an ester. And I can also convert it into an amide. And so these are carboxylic acid derivatives. And the reason that all of 4 of these are called carboxylic acid derivatives is that when you treat each one of these with either H plus H2O or hydroxide and H2O, you will end up forming the carboxylic acid again. So a carboxylic acid derivative is something that hydrolyzes into a carboxylic acid. So it undergoes what is called hydrolysis. And hydrolysis is when you use either base or acid and water to cleave something with water. It means cleavage by water. Okay, so these are all of our carboxylic acid derivatives that we're going to talk about in chapter 25. And we're going to go through their details, and then look at the reactions of each one of these derivatives. But what I want to talk about today, just at the end here, is I want to compare and contrast the reactions of carboxylic acids and derivatives with aldehydes and ketones, because aldehydes and ketones were in their own chapter for a reason. And so if we look at the idea of making the group that's attached to the carbonyl group a Y group, and that Y group could be an H or an R group in the case of an aldehyde or a ketone. Or it can be an OH group if it's just simply a carboxylic acid. Or it could be a Cl or basically a carboxylate group or an OR or an NR2 group. So all of these can be Y groups. Here's the difference between those two sets of reactions. So we knew that when we added, for instance, a strong nucleophile to a carbonyl, let's say with a Y group on it, the nucleophile will come in, will form the O-, and the nucleophile will add. And let's just say that's either a nucleophile that's either strong with a negative charge, or if it's a weak nucleophile like water or alcohol, in other words, it has an H on it, we need H+. But what we would do is add the nucleophile to the carbonyl to form that molecule. Now what would then happen is the O- can bring its pair of electrons back down and kick off the Y group. If this is a leaving group, then Y will leave and will reform the carbonyl, and the nucleophile will have added to the carbonyl group. So think about what happened in each case. When we had the Y group being a carbon or hydrogen, in the case of aldehydes or ketones, number one, we ended up with an equilibrium when we added a weak nucleophile. So when we added a weak nucleophile, we ended up with an equilibrium reaction. Now, Y never leaves. When we reacted that with a strong nucleophile, what happened was that we ended up forming so if the nucleophile was strong, like an H- or an R-, we would end up forming the alkoxide, and there's no way to bring the pair of electrons back down because this isn't leaving, this isn't leaving. So we would wait for H+, and we would form our alcohol. Right? And that's what we did when the nucleophile was strong, like an H- or an O-. When the nucleophile was weak, we ended up forming an equilibrium where we would form the hemiacetal or hemiketal or hydrate. But this Y group with an aldehyde or a ketone never left. The difference in this reaction with these carboxylic acid derivatives, or even when there's an OH group as the Y, is that all of these groups up here, all of these Y groups, they could be leaving groups. And so if they can be leaving groups, then that changes the reaction so that when the O- comes back down, if Y can leave, I'm now going to do what I would call a nucleophilic substitution, and this is actually called nucleophilic acyl substitution because now I'm doing it on a carbonyl. Okay, so that's going to be the difference as we set up the next two chapters. Aldehydes and ketones, we never did that last step because there was nothing down here that could leave. When we added weak nucleophiles, we just, again, spent our time going back and forth here in the equilibrium, but we never lost the Y group because it was a carbon or hydrogen. Now what's going to happen when we get to forming these carboxylic acid derivatives is that the Y group can leave. And oftentimes it will. So that's going to set up chapter 24 and some of chapter 23 here as we react the carboxylic acids and their derivatives with strong and weak nucleophiles. Okay, so that's where we will end today for today's lecture. So the quiz will be over those review reactions. So there'll be 14 questions. Anything else I want to add, I'll add on the next online quiz. Okay, so that will be the end of today's video.